Can you guys see my screen on Zoom? I'm looking for you. Okay. All right. Connie, you might have to try out something else if it's not working. Uh, maybe it's your screen. All right. Okay. So going back to our previous discussion on IDF. Any thoughts on this? All right, so we had two formulas. So one was adding one and then doing log of n by n. So the idea of doing n by n is, when you have the words occurring in all the documents, essentially it turns out to be log of 1, and log of 1 is 0 for any value. So that's why, when you try to do TF-IDF, you're not multiplying it by 0. So in some sense, adding that 1 sets up a lower bound of the value that you can take. The other approach that was there was doing log 1 plus n divided by 1 plus n, or 1 plus n divided by n. So in those scenarios, what used to happen is it ends up setting a lower bound again on the limits. So those are the two ideas why this structure is there. There is no really right or wrong way of using it. It's just some softwares or some tools prefer it the way it's there. All it does, it sets up a lower bound of what value TF-IDF can take. So if your words are set in all, your bottom, the lowest value that it can take is going to be 1, and the highest value is going to be log n, where you just have it occur in one document. So that's how that structure works. Beyond that, that was the piece that we had. Now, with regards to papers, did you guys end up reading the papers that I shared about? Are there any questions around it? Anything that you want to ask up before we get started? Can you put on Slack or the chat in Zoom? Any questions on the paper that I had shared? Did you get a chance to look at it? Any doubts about the paper? None? Okay.
And I just kind of just maybe don't use copy. And
But it, basically you have to keep trying it based on what you end up doing as well. So it's kind of case by case, but NLP is one thing where you have to try out something before it works out. If not tried, our as well. But the first thing that for jumping into probability, the best answer or the best approach to go get started with, at least in my opinion, is decision trees. In my opinion, they are one of the easiest ones to understand. Even with the latest deep dives or the latest technologies, the concepts are still fairly same, and it's one of the most intuitive ones to understand once you get a hang of it. So today, let's start off with very basics of decision trees, and then go from there. Again, if you get stuck anywhere, post on Slack.
have you used this machine?
All right. I have muted all of them. This machine muted. I just muted it. Is this better now, SE?
Is it better now?
Okay, I have forced muted everyone. Thank you. Sure. All right. So do you still want to go through the questions on, no, there are no plates here. Do you still want to go through the questions around IDF, anything that we covered last week before I jump into decision tree design or a classifier design? All right, looks like there is no comments. Okay, let's get started with decision trees. Please post on Slack. On Zoom, although the chat is good, it just makes it harder to manage two things. All right. So we are going to again look at classification because in some sense, when we were doing sentiment analysis, we were trying to kind of work through sentiment, which was a version of classification. And for this one, we are going to make use of decision trees. So as we get started into decision trees, one of the things that I always like to do is, kind of look at what are decision trees, right? So of course, classification with decision trees is not the only way of looking at it. Typically, there are a lot of different uh, algorithms that are around there. But decision trees are one of the most popular ones. If you look at Kaggle, everybody starts off with light GBM, XGBoost, more recently Cat Boost. The Cat in the Boost, which is again a similar version of a gradient boosted world, is it has special ways of handling a lot of categorical features. And for categorical features, I'll kind of come back to it later, when we have done some algorithm designs and uh, kind of work from there. But having said that, right, decision trees is one way of doing classification. Sometimes simple rules can work out as well. And then, mathematical formulas are some of them. So let's look at this link. So this was one of the links which I had shared last week as well. It's called R2D3. It's similar to your Star Wars R2D2. It's just R2D3. D3 is a visualization library. Uh, so let's just look at this versions as well. Yes, I'll post this link just now. Give me a moment. So posting the link on Slack on NLP Live. Oh, sorry, wrong link clicked. All right, so I'm going to kind of again walk through this page itself. Um, and kind of start to build some intuitive understanding around this piece. Can you guys see my screen? All right, so let's go through this. I prefer going through this website. It kind of gives you a lot of intuition around around decision trees and something that you can play around with. And then I'll kind of do the same experiment in Excel, and then kind of start to build some of the mathematical intuition around some of these things. All right. So what we are going to do is build some intuition where we are going to determine based on various attributes of a home whether the house is in New York or San Francisco. San Francisco is given in green while New York is given in blue. So now what they are looking at it is elevation of the house. If you know that San Francisco is relatively a hilly area, one of the crookedest streets that you will find in the world is in San Francisco. So now what I'm going to look at it is just each line represents a single house at a particular elevation. If you look at your y-axis, that's just your elevation. For New York, it starts at, it ends at about 239.5, while for San Francisco, it goes up as high as 744. So now if I were to say that, hey, let's do a simple classification with just this one attribute, what is the cutoff point on elevation that you can give? There are a couple of options in there. So the question is, what is the elevation, cutoff elevation that you can use for classification? Just a simple thought. You can post your questions on Slack. One thought is 250 using elevation, 120, 240. Anything above 239.5 is San Francisco. Yep. So yeah, so that's a quick idea that anything above this value, because nothing ever exists in New York, most likely it's going to be in San Francisco. That you can be 100% sure. Or I could take a value that's, I have a big gap between the top value. So I could take a value which should be around 150-ish something. I'll get some error, but again, with very good confidence, I will be able to do that. So that's a very intuitive way of defining a standard split that will tell you whether a house is in New York or San Francisco. Is this part clear of how we kind of did our first cut of classification? All right, let's move on. Now let's add another nuance in here, right? So we kind of saw that, hey, I added elevation. Now on my x-axis, I'm just going to split it out and add price per square foot, which is essentially going to be my x-axis. And my y-axis still remains the same, which is elevation. So the point that you see on the top is essentially the 744.8, which was the topmost house over here. Now, if I were to kind of do these factors, right? Now, these two become essentially what I called as features, right? Which are, in your traditional machine learning sense, are also your variables. Now, if I were to kind of separate these out again and then say, okay, can you help me draw boundaries around both my elevation and my price per square foot? Where would I draw it? So first one was, it was very clear that I could draw it at around 239.5 or around 240. That just gives me this point. How about my price per square foot? Post your answers on Slack, and then let's see. So I have one green dot that's around here. 1780 is correct. 1776 is also right, depending on how you are going to round up your values. And now you have kind of started to build the intuition. So you're saying that anything beyond that is going to be all right. Kaushik, 180 will be essentially for a value that's going to be different. Okay, 1800, that seems about right. So some of you are kind of putting some sort of buffer just in case kind of thing, but let's work with the data that we have, right? So typically when you kind of work with these sort of things, you're not able to determine exactly what those values are going to be. So setting up simple values is going to be hard. So let's start drawing the boundaries. So now I have kind of done with my two predictors, two variables or two attributes. I've kind of determined my two boundaries, which are given by my green square and the blue square. So what my blue square says that if my price per square foot is anything greater than 1776 or 1780, that's very likely to be in New York. Conversely, any value that's greater than 240, it's very likely to be in San Francisco. So now we are starting to build a very interesting model. But let's start to see, do you see any other similar techniques or data that show you similar structure as well? So what we typically do in your machine learning model is we created a chart which was elevation, which is my topmost row, and my price per square foot, which is my last column, right? So the value, the chart that we drew was in the top right corner of my scatter plot matrix, right? Do you see any other chart that looks almost similar to price per square foot and elevation? Post your answers on Slack. Any other chart, any other thing that you see interesting that could be something that I could use with very clear boundaries on for building my machine learning model, or in this case, a decision tree model. First row, fourth column. So first row is elevation, fourth column. One, two, three, four. Yeah. So this one, which is also price. So price per square foot seems to be about right. They seem to be similar. I can delineate very well. Any other that you see? Price and elevation. Yep, that's about right. Square foot versus price. Square foot versus price. That seems all right, but yeah, I could. Well, I could do New York. So one of them suggested square foot versus price, which is the leftmost one on the bottom, which is somewhere here. You can delineate New York, but probably not San Francisco, because San Francisco is all clustered around a central value. Anyways, so let's kind of go through that. So let's come back to our previous structure that we had, where we said, all right, we are just going to probably look at elevation itself. Now let's change the perspective, right? So now instead of drawing those bar charts, now let's do something which we call histogram, and let's see where these values land up with. So if I start off with 240, right, which is a value that almost all of you suggested, just by this attribute alone, right, I would get 63% of these values to be correct, right? So on my left-hand side, the bar, the pie chart that you see, I got a mix where I could say New York and San Francisco. But on the right-hand side, the circle that's all green, that turns out to be only San Francisco. So I could clearly mark out San Francisco and do a pretty good job, right? So just by looking at that, I just got 63% of the values to be correct. Now let's go through the other extreme, right? So now if I say that, screw everything, I'm just going to put 0 square foot, and then everything ends up being in San Francisco, right? So New York apartments are also San Francisco. So just by doing that, you will still end up getting 56% correct. So this what sets up the baseline of your model, right? So a single attribute saying that, okay, I'm not going to look at anything else but just one variable, and I'm going to say that everything is in San Francisco. It ends up at 130, 56% correct, right? So that sets up your baseline, saying that even if I don't do anything and say everything is going to be in San Francisco, with the data set that you have, you'll be 56% right, which is typical of some of the data sets that you are going to see, which are going to be balanced. But I think we can do something better than 63%, where we set the elevation threshold at 240 versus elevation at 0, where we got 56% right. So now let's play around with this. And if we keep playing with these values, so if I do 91.9, I get to about 82%, which is way better than what I did here. So on the left-hand side, I got a few errors where some apartments that are in San Francisco got classified as New York. And the same thing goes for San Francisco, which is on my right-hand side, where there is a lot of green, but some of the apartments that are in New York got classified as San Francisco apartments. So we figured out doing these sort of splits, and we got to a correct value as we built along. Is this part clear of how we played around with these values to come up with an approximate accuracy for a binary classification? Any questions you have? Post it on Slack. I'll wait a couple of minutes. If it's clear, just type yes, no questions. So at least I know there is none. This part is like, I just want to make sure that you guys understand this piece, because this is something that will keep coming over and over again, and develop formulas on, how do we determine the best split. So before we get into the best split, I just want to make sure you understand intuitively, what the split is trying to do. Do you guys understand what the split is trying to do? No questions? All good? Yeah, some questions on Zoom. Please try to post it on Slack. Makes it easier. All right. So I'm going. There are only few folks active. Anyway, let me go on. If you have a question, just post it on Slack. We are live on NLP Live discussions on Slack. All right, let's continue. So once I keep doing that, right, my next variable that I'm going to do is price. I determine my price boundaries, similar to price per square foot, because these two were the options that some of you guys pointed out, and I determine what my best boundaries are. So I start off with elevation, right? Then I move on, do a partition of my data. So everything that got classified as New York, which was on my left-hand side, I move to the left-hand side of my branch of the tree. Everything that got classified as San Francisco, I move it to the right-hand side of the tree. So now I work with the data that's on left and right. Now I don't look at the overall population, and then start trying to do the same things which I did for price and price per square foot, right? So given the data between the splits that I have, what is the right split going to be, right? So I kind of determine that for my left-hand side. The same thing I do for the right-hand side, which is essentially all the apartments that are in San Francisco. A very few of them were in New York, and I build it up, right? So now I keep doing that and start building my tree to a point where I have, okay, let me come back again. So the first part was elevation, right? So we said that elevation at about 92 feet is anything less than equal to 92 feet. I move it to the left branch, where I come back and say everything is in New York. While on right hand side, I say everything greater than 92 is going to be in San Francisco. Now, I have already partitioned my data. So everything that gets classified into New York, including the apartments in San Francisco, moves to the left-hand side of the branch. Everything that is in San Francisco, including the misclassification of apartments that are in New York that got classified as San Francisco, gets moved to the right. Now, I picked up price per square foot and price, and I do the similar exercise of trying to find out the best split at each point. So now on my left-hand side are all the apartments that got classified as New York. And you can see that most of these are values that are blue, because blue was New York and green was San Francisco. So there's a little bit of green, but then for most part, it's going to be New York. So now I try to figure out what's the best price per square foot, the example that we did earlier, and try to find out again a best split. Same thing for the right hand side where I do with price. Is this part clear before I move on? All right. So I keep doing that. So I keep classifying my left-hand side as San Francisco, right branch as San Francisco, left branch as New York. So at price per square foot, everything that's less than that threshold point is going to be classified as New York. Everything that's on the right-hand side of the branch will get classified as San Francisco. The same thing on the price as well. Left-hand side is going to be New York, right-hand side is going to be San Francisco. So I keep doing that, keep adding more and more variables to a point where my values become pure. By pure, I mean that, there is no further splits that I can do, right? So, when these values in circles, the larger the circle, the more of these values sit in there. And you can see that your decision tree is kind of uneven. right? So not all of them have enough splits. So we went on to a point where the node became, the leaf nodes became very pure, right? Which means that there is no further splits that I can do. But there's one problem with this. Can you see what problems are you going to get here by going down to a point where your node becomes pure? Post your answers on Slack. Yeah, that's absolutely right. So you could end up with overfitting, and overfit is a big problem. So that's something that you have to think about as you kind of build a decision tree. So we'll kind of develop that intuition of how do you kind of take care of overfitting in a decision tree. So if you let your tree keep growing to a point where it becomes very very pure, the chances are that you might end up with overfitting for that. And that's Ankit, that's right? Your data becomes scarce for a particular category. So in case you have imbalanced data, that's going to be a big problem going in because you don't have a lot of variation in the data set for it to do a proper classification. So now let's look at your prediction, right? So now you took everything that was sitting in there, and with all the levels of tree, you got your training accuracies at 100% because you went on till your node became pure. But that's not how a typical machine learning model works, right? I wish I could get 100% accuracy all the time. So what I typically do in doing machine learning models is I'm going to keep some data, separate it out and keep it, I'm not going to use that for building my machine learning models at all, right? So I'm going to use that as my validation or even test sets. Now I kind of take that remaining data and then pass it through this trees, right? Which is what you end up seeing, right? I end up with a test accuracy of 89 or about 90%, right? Now it learned a lot, but compare this to your first query that you got by building just a simple value, right? You were at about 83%. And then by adding so much complexity, you added like about 6 to 7% in your model, right? So sometimes keeping your models simpler could be a way out instead of adding a lot of complexity and then potentially overfitting your problem, right? So overfitting is a problem that we'll tackle. Um, but this is an idea of building a decision tree. Is this part clear? Like, are you able to kind of visualize how a decision tree is built, how these splits were done, and what is the concept of overfitting, and then the concept of test accuracy? All right. So now, we left out. So how do you determine text accuracy? So basically what you end up doing is take all the data that you kept aside, which was never ever used for building your model, and you pass it through your model. Because you knew what was your original classification, right? Because that was the data that you kept from your original data set. You now know which of these apartments were in New York, which was this apartment in San Francisco. So you had your decision tree model, and then essentially you came back and said that, okay, here's what the tree predicted versus what was the actual. So now, once you know your actuals, you are able to determine what your test accuracy is because you knew what your true answers was, you knew what your model predicted. So, the number of that it got wrong becomes your test error. The numbers that it got right becomes your test accuracy, which is currently at 89.7. Does that answer your question? All right. So, so this is how a decision tree is built, right? Uh, but one of the key things that we had earlier, right, is when we were determining split, we were actually playing around with these values, right? But when you build big models, you're not going to be sitting around and playing around with these values to determine, hey, what is the right split? So there are a lot of these ideas that are in building decision tree models. So let's look at a couple of them, right? But before we get there, right, I just want to cover some theory. So let's go back to, let me just share my whole screen. It just becomes easier. All right, so I'm back into my PowerPoint, and we did this example thing before, right? So I was playing around with the cursors and said, all right, tell me which one does better. And, we just played around with it and figured out, oh, this particular point gives us 83% accuracy. This point gives me 56% accuracy. And we are playing around with that, right? So how does a decision tree will make this decision? What are the formulas associated with that? So there is this concept that we call as information gain, right? Which tells us which split it needs to make. What is meant by information gain, right? So when we did a split at 95, right, which got us to around the accuracy of 83, right? We gained some information about the data set that said that if my elevation is greater than 95, the apartment is in San Francisco. Anything less, most likely it will be in New York. So you gained some information, right? So that's the concept that we'll build along. So there are two theories that sit in there, and this is something that you will find up in a lot of decision tree based models. So the first one is called Gini. It actually comes in from the economic theory. When you're looking at inequality and stuff, they'll talk about Gini index. And the other concept is entropy, right? So Gini is simply given by this formula where you're going to say 1 minus the probability of having a given class in your data set is going to be, so basically you sum it, so you square that probabilities. And then you go back and look at, and you sum it up and you subtract from 1. So that's your Gini index. And then the same thing for entropy. Well, instead of doing square, I'm multiplying Pj, which is what you have in the previous equation. So I did Pj times Pj. In entropy, I do Pj times log 2 of Pj, right? So this is there. If you don't understand probability, right, a very simple way of to look at it is percentages. So when we did 0, my first percentage was 56%. So my probability is going to be 0.56 for New York, sorry, for San Francisco, and 0.4 and 0.34 for New York. Right. So basically, I'll take a sum of squares, subtract it from 1. That's going to be my Gini. So basically, what I need to find out is at which point my Gini index becomes the lowest, right? Because my Gini index becomes the highest because this is the value that you want to minimize. All right. So before we get there, I prepared an Excel file that we can go and practice with. I'll share this Excel sheet as well. But for now, I just, okay, let me just share this Excel sheet. This becomes easier, posting it on Slack. All right. While it's being posted on Slack, it's the same data set that you saw earlier. I wrote up some few formulas that will allow us to play around with it. And I'm going to go through the Gini index. And then I'll download the Excel spreadsheet in a moment. In the meanwhile, let's go through how we work through the idea of Gini index, right? So this cursor, there are no macros in here, so you will be able to see the formulas and play around with it. So what I'll do is I'll set up some formulae, right? This is the threshold of ESF. So I'll set it up at around 2000, right? Let me just override it so it becomes easier. So again, similar things, right? Left hand side becomes New York, right hand side becomes San Francisco. In this one, my right hand side is on the top, which is marked as branch 1. while everything that's in New York is marked as branch 2. Now, I said that everything that sits in below this threshold is sorry greater than this threshold is sitting in here. So I got about 437 at individual items, uh, some of which were in San Francisco, some of which were in New York, right? But this is a branch that I'm going to come out and say that this is in San Francisco and the rest of them are in New York, right? Depending on how you want to do it. So now I take a percentage, right? So I say 172 divided by 437, that gives me a percentage. I do the same thing for San Francisco. Now I take a square of percentages, which is nothing but square of these values, right? And then I sum it up. And then I said my Gini score is 1 minus this particular value. But remember, I also have a second branch, which is something that I need to do the calculation. So I do the same. So everything that's sitting in here, which is going to be New York, the next one is going to be in San Francisco. I calculate my percentages. So percentage of apartments that are in New York as total of this particular branch, right? And I take a square of percentages, calculate the sum of squares, calculate my Gini impurity, and then I take a weighted index of these values. Why do I take weighted index? Because it's not a 50-50 split, right? On one branch, I have 437 values. On the other branch, I have 55 values. So I can't just take an average of the two. I need to take a weighted average. So again, the formula is straightforward, where I multiply those values and then divide it by the weights, right? So now I got to my weighted Gini index. Now this is a value that I need to minimize. Now my question to you is, play around with this PSF uh, in the file that I shared across and post on Slack what is the value of PSF that minimizes my weighted Gini index, right? So play around with this and see at what value it becomes the lowest. Hmm? So download the Excel file which I posted on Slack and play around with the values in the Gini tab and tell me which PSF gives you the lowest weighted Gini index. And take a break for that, grab some water while you guys play around with it. Any other values that you guys can think of? Play around with it and see. One 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 four gives me a Gini index of 0.357. If I decrease it further, it goes down because I've kept the stops to be different. 1160. That's too high. 1110. 1093. 338. I think that's the lowest value that I've got. Let's try 1087. Yep, just about that. Now again, there is a lot of rounding going on, so some of you might get for the same value slightly different. How about entropy? Does my answer change if I change the values to entropy? What values do you get if you end up doing with entropy? Same? Okay. 1081. Yeah, looks like it's around to be the same values, right? But your weighted entropy turns out to be different. So did you guys understand how we use entropy and or Gini to figure out these algorithms, right? So this is what is used with a lot of decision trees to make a decision for the split. Is this part clear? Right? And then you can see that when you are at a different value, you actually get a pretty decent amount of values that are either in San Francisco or in New York. Yeah. Everybody clear with Gini and entropy? Why? So the question was why the weights needs to be lowest. Because when you gain that information, right? Basically, your randomness or the way Gini is defined is that you found some information. So basically, your randomness of the data goes down. So that's why the weight needs to go down. So essentially, you are minimizing for that Gini and entropy values. And the other mathematical way to think about this, right? So at what point, so let me go back to the PowerPoint, right? So let's just look at Gini for a moment, right? When will Gini be equal to 0? When is Gini going to be, when my sum of p square is going to be equal to 1, right? So I need to get, so if I take a binary, either I need to get 0.5, zero point 0.5, or similar values that's going to get me to that value, right? That's when your values will end up turning to be 0. But that's a difficult way to look around it, because only way to do it is, turn either way, either one of them to a very, very high values, right? Which is again going to be very hard. So your best way, again, from a mathematical perspective, is try to get to that value that will reduce those values into 0. All right, you got this part? Okay. But even now, right, I didn't really answer your question that I asked earlier. Is I was still playing around with those cursor values, right? I didn't I didn't optimize it. I didn't do any mathematical formula around it. I just said that give me a value that minimizes Gini index or my entropy to 0, right? I still was playing around with different values to do it. So how do decision trees solve this issue? Any thoughts? They certainly don't play around with this. Any other thoughts on your mind? Still, so the question is that right now we were, just what we doing. we were playing around with this value, which was similar to what we did when we went on to the web model on R2D3. So in a decision tree, right, I'm not again going to be sitting around and playing to figure out what's the best split that's going to come around, that's going to give me the best value. So what are the different ways that, in your opinion, that are going to be a way where a decision tree can find out the optimal split? Feature importance is not relevant at this point. Gradient descent, yes, but I'll leave it that for later. Uh, Something more simple. Minimize the loss. So that's an idea around gradient descent. Minimum value, yeah, but how do you figure out that minimum value? Attribute selection, not yet. Hold that thought, Sandeep. We'll come to that point in a bit. Mean, not so much. Differentiation, again, going back to the gradient descent approach where you make sure that your loss is differentiable. But we'll come to that, right? That's a little bit advanced. You are right there. I want something more simpler. Median, nope. So splitting, yes, it's for splitting those values, right? So how do I determine the best split, right? I was playing around with it. So the idea is how does a decision tree figure out what's the right split to make? Yes, something that maximizes the information gain, max the probability of any one class. That's the objective that we want to do, right? We want to maximize the probability of one class that's being done. All right. So some of you got the answers right, but that's for algorithms like the more state of the art at this point. XGBoost, like GBM, CatBoost, they use differentiation, but we are not going to use differentiation. We are still learning how to split it. So one of the ways to do a split is going to be doing it randomly, right? So what some of these algorithms allow for is that given a data, right? So given, let's say in this scenario, PSF, I'm just going to split it 128 times or 64 times or 256 times. Whatever number that I can set, I'm just going to set it up, right? And for each of that split, I'm going to calculate, again, the similar exercises that we ended up doing, Gini impurity and weighted Gini, Gini impurity or entropy. I can do that calculation. I have to pick one. I cannot pick both. Right? So I'll pick one. And for each of that split, for a given feature, I am going to calculate the weighted Gini index. And then pick up the split that gives me the lowest value. Let me repeat. So I'm going to randomly split ESF into 128 randomly split points, right? And for each of that split, I'm going to do the same calculations here that you see on the Excel sheet and calculated my weighted Gini index, or if I'm doing entropy, then my weighted entropy, and use the split that gives me the lowest value. Is this part clear? So I randomly do a split, 128 splits, and then pick the one that's more important, that gives me the lowest value. Do you guys get this concept? If not, I'll repeat again. So why particular 128? That 128, you can pick any number. Typically it's in the multiples of 2, but that doesn't prevent you from putting 127 or 64. Okay, so some of you are asking me to repeat, so I'll repeat again. So for example, I have PSF, right? So for PSF, I'll randomly pick 128 splits, right? You can pick whatever number that you have, right? I can go with 10, 16, 32, 64, whatever those splits are, right? So for each of the split point, I'm going to do these calculations, right? So for each split, I'll get my weighted Gini index, and then I'm going to pick the split that gives me the lowest value, right? Is this clear now? Okay. So that's one way of looking at it. So based on one question that was asked earlier, why 128? Why 128? Let me put that question back to you guys. What happens when you put a higher number, let's say 256 or 512, as compared to a lower number of, let's say, 8 or 16? What's going to happen when you pick the number of splits to be a higher number as compared to a lower number? What's going to happen? Yes, of course, it takes longer to calculate. So your each split is going to get slower and slower and slower. And imagine, right? Every layer you're doing, you know, a power of two. So the first layer you do, you're doing one calculation. The second layer you're doing two calculations. The third layer you're doing four. So the more of these layers you have, right? And at every point you're doing a split. So it's going to get more complex. No, Sandeep, there's nothing to do with optima yet because we still don't know what the optimum is going to be. Better accuracy, not quite. Um, we are still on a single node, so don't think about accuracy, right? We are still talking about a single node. So what happens on a node if I do a lot of splits versus compared to a less number of splits? So when you do more splits, yes, exactly. Ochin got it right. Uh, when you kind of do more splits, the chances of you finding the lowest or the correct value is going to be higher, right? Because think about it, it's all randomly done. So the more splits I do, the higher the chances of me trying to find out the right value, right? So that's how it works. So this works very well for quite a few algorithms. There is a class of algorithms that we'll deal with later. It's called ExtraTreeClassifier. Now, ExtraTreeClassifier doesn't care about doing splits, right? So all it's going to say is like just randomly take a split and be done with it, right? So your tree calculation becomes much faster. While if you think about random forest classifiers uh, or some of the more current classifiers, they will do multiple splits. So even Azure Machine Learning Studio will allow you to say, how many splits you want to do. And the default value that they set up is 128, right? So that's a configurable value. But some algorithms allow it. Some say that I'm just going to randomly pick a value and just go with it. So the idea where this value becomes configurable, the higher the number, the higher the probability of you getting towards the lowest point. But it's going to take longer to do it. But this is not a value that you should worry about most, because if you build sufficient number of trees, right, or enough depth of those trees, this splits will become irrelevant because it's going to do that. Now over here we talked about just a single feature, but I wish again your real life doesn't have a single feature. Most likely it's going to have more than one feature, right? So now how do I pick which feature do I do a split on? Any thoughts? So let's say in this data set, I have quite a few features. So I have so this is in San Francisco. This is my class. I have beds, bath, price, year build, square foot, elevation, price per square foot. Right. So I already have 7 attributes. So which attribute am I going to pick first? Random. Pick. Go through all of them. What are your ideas? The one that gives the best balance for split. So how are you going to figure that out? You will loop it first, balance counts, the one that, yep. So most of you are kind of getting right. Is one way to think about this is look at all the features and calculate again for each feature. You'll go into 128 splits, calculate the Gini. You'll repeat this across the board. So for each one, you'll pick the one that's the lowest. And then across the feature, you'll pick the feature that gives you the lowest Gini or entropy value. Let me repeat. I will do this 128 splits, for example, and calculate my Gini for each of these features. For each feature among the 128, I'm going to pick the one that gives me the lowest Gini value. So for these 7 items or 7 attributes or 7 variables that I have, I'll get each feature, each one having its own lowest Gini or entropy score. Okay. Among these 7, I'm going to pick the one that gives me the lowest Gini score. So that's one way of looking at it. Is this clear or should I repeat? Yes, so only one feature will be selected because in a decision tree node, the split is made on a single decision point. So think of that as your if then else criteria. So now you're trying to find out what is that criteria going to be. So only one feature will be selected. All right. So there are a lot of ideas in this. So one, again, think about this, right? Once you have a lot of attributes in here, then you're going to do this 128 split times a number of attributes. One other thoughts that are in there is going to be with picking up randomly some threshold of value. So let's say, in this value, I have 7. So I'm going to take a square root of 7. Right? So it gives me like a value of what around 3, depending on how you round it up. So I'll randomly pick 3 values and do a calculation around that. So I'm going to take square root of 7 because I have 7 attributes, and then round it up or round it down, right? Depending on, again, changes from structure to structure. So I'll randomly pick beds, bath, price, whatever I can, do my 128 splits, and then work it out, right? I keep randomly doing that. But when you kind of do that, you have to make sure that you're not kind of working that out. So that's another way of tackling overfitting when you build multiple trees. But we'll kind of tackle this in a bit. So is this part clear of how a decision tree works this out? Okay, so now that you have understood, how a decision tree is being made, so I have one question for you, which I asked earlier, right? So when we were looking at this on the website, we said that, the nodes became pure. So that's one of the criteria when the tree stops building it. What do you think there are other conditions that I can put on a decision tree to say, okay, this is enough calculation, stop? Because think about it, every layer, I keep increasing the complexity of these calculations by a factor of 2. So my question to you is, what conditions I can tell the algorithm that stop building the decision trees or stop growing? Max depth, yep, that's right. The number of values, that's also right. What else? What else can you think of? So your depth is the number of levels of the decision trees that you go in. So for example, the maximum depth is probably somewhere around here. So I have 1, 2, 3, 4, 5, 6, 7. So this decision tree is 7. I think so. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So Yep. So that's about right. So we go up to a point where we cannot split anymore. So that's one way of looking at it. So you can also limit saying that if you don't have X number of data points, uh, you can stop at that point in time. So that's another way of looking at it. Minimum amount of data points. Yes, that's about right. So these are different ways in which I can set up at to what depth you can going to go with it. Accuracy may or may not increase. So that's another way of thinking about it. So we'll kind of talk about that in a bit. Right. So those are the conditions that I can put into a decision trees of saying that here's a way of looking at it. So the question is, if most of the attributes give around the same entropy, what does it say about the feature selection? In a lot of these scenarios, right, if you get a tie between any one or more features, you randomly pick whichever one and continue with that, right? So there is nothing fancy that goes around. And then something that you will understand, which we'll cover next, is why that randomness really helps in bringing stronger trees. But before we get there, right, I just want to make sure you've understood, how this decision tree is built up, and what factors go into there. All right, so I'm going to open up a decision tree classifier, right? And what would happen? So hold that thought, Ankit. And if I don't answer it towards the end of the session, we'll talk about it. So anyway, let me try to answer that. So there are these algorithms that don't really care about minimum Gini. And they just say that, all right, I'm just going to pick randomly a split, whatever the value comes in, I'm going to go with it. So those are the concepts that get built up, and those are the answerable concepts. So just hold your thought on that. I'll surely cover it, before we end the day. But now let's go back and look at decision tree classifiers. And now let's go through some of the parameters that you can set up that will help you understand what's really going on, right? And try to visualize the concepts that you have learned so far, and see if you are able to answer some of them, right? If you don't understand any of these values, message me on Slack on NLP live discussions, and then we can take that up. All right. So the first one that is there is criterion. So the value is Gini. The other is entropy. Now we did those examples, so that becomes very clear. Is that right? Okay. The next one that we have is the splitter, right? So when you're picking Gini or entropy, I said that pick the split that's the best, right? And this is where your values of number of splits come into the scenario, right? But see, I think Ankit had asked that question before, is what happens if I don't pick it, right? And that's a value that's also an option. When you pick random, it will randomly just pick a value and get going with it, right? But it works. As you kind of start building deeper and deeper tree, it will kind of do it. So that's another way of building faster trees. Max depth, right? So this is also a concept that you now understand, that if you keep going deeper and deeper and deeper, the chances that you will end up overfitting, right? So you can control your max depth based on your knowledge or your structures that you know about. The next one is minimum sample splits, min sample split, right? The default is 2. So it will keep splitting the tree till it has the 2 values beyond which it's not going to, minimum number is going to be 2. So if it's 2, then it's going to do the split, right? So it will keep on doing that. So that's another way of controlling how deep your decision tree goes. Then minimum samples per leaf. So when you do the split, right, how many samples will turn on at each leaf point, right? So that's another way of looking at it. This is a little bit complex because if you are now setting weights on certain attributes, uh, which is where you say that I weigh I weigh more of these things, these observations more, and some of these less, and that's a concept that we'll deal with slightly in a bit. But when you kind of start to say some observations are more than others, then that's another way of looking at weighted fractions. Max features, right? So this is where we kind of again kind of looked at it, right? So if you set default as none, which means everything will be considered, right? There are a lot of these values where auto, which is what we did, right? Which is what I kind of shared with you earlier. I can take square root, right? So I can take square root of number of features, and only those features will be considered randomly picked and considered for the split. I can also do log 2. If you set none, then all the features get used for identifying the splits. So I'll repeat again. So if I set the max features to none, or any of these values. If it's none, then it's going to take all the features, and based on the criteria that I said earlier, which was Gini, it's going to pick that criteria and find out what is the best split for each of these features, right? And pick the feature that gives you the lowest Gini or entropy score, or whatever criterion that you have set. So these are the features that you can end up controlling. Random state. As you know that a lot of these values, like the number of splits, like I said, it's going to be random. So where it gets done, if you want to kind of have that tree going to be repeatable, then you set up a number associated with that, whatever number it's there. As long as you put your number, the tree that's going to happen is going to be reproducible, which means that the same structure will get built. And these are some of the other values that you can say, hey, minimum impurity decrease. I think one of you mentioned that, if I don't get a certain decrease in impurity or information gain, then I'm going to kind of do it. Minimum impurity split, again, this factor has been removed, and minimum impurity is what you need to kind of work with that. And pre-sort, right? So when you sort those values, finding the best split becomes much harder, much easier. So that's another way of looking at it. So one question is that, if I pick square root or log, some features will be completely ignored. If you build a tree with sufficient depth, then some of those features will get used. So because it's picking randomly at any point in time, it's not like one feature consistently will get used throughout the trees. It's very rare. There is chance of you doing that, and that's why typically in some of the Kaggle competitions, when you are trying to kind of build multiple models, you play around with your random numbers just to kind of make sure that something of this has not really happened. And if you get the same answer, then you know that most of your features have been considered. Does that answer your question, Arti? Yeah. Does this give you a good flavor of how a decision tree is built? Do you understand now all the attributes that go in there, and now you can make a judicious decisions about it? Or do you want me to repeat any of these ideas that are not clear? Type your message on Slack. I'll just wait for it. Looks like all good. What is the ideal value of max depth? That's something that you have to play around with, right? Your whole idea that all these factors that you are controlling essentially give you a handle on how to prevent overfitting, right? Some of these values are kind of default set as very high, so you have to make sure that you're not overfitting. So these are some of the parameters that you have to train using your test set or validation set and your training set, and then you figure out what is the best factors for some of these things. So that's something that you have to find out, and that's where your hyperparameter optimizations come into play. There's no magic value for doing that. But the idea of this is at least now you understand what factors to play with, and you don't have to tune everything together. Just a few of them will give you enough factors to give you an idea. But hopefully now you understand and now you're able to visualize what each of these attributes do. All right. So now that is clear. So now let's look at, somebody had mentioned about feature importance. So let's look at what is feature importance. All right. So it's an important concept, but let's understand what we end up doing at each point in time. Right. So what I'm going to do is, build an hypothetical tree. Right. I don't care about values at this point. So I started off with 100 data points. I did a split on elevation. I got a 60-40 split. 60 went on my left hand side, 40 went on my right hand side, right? So at my node number 2, I split on PSF, and then it did some certain split. On the right hand side, I split on price. I got a split between 10 and 30. Then again, I do my feature selection based on the criteria that I set. Then I do a split on PSF, right? And I keep doing that till I reach one of my terminating criteria that I've defined before. Now, on node 1, I got 100 data points. My feature is elevation. So my information gain, I've just kind of gotten this because every point you're trying to minimize this was 0.3, right? So this is my weighted Gini or weighted entropy, right? Whatever it is, we're going to talk about information gain. So my total gain that I got at this point was 100 times 0.3. That got me to 30. I go to my second node. My second node only got 60 points, right? Which was the split based on my elevation criteria. My left hand side only got 60 points. Then I did a split on PSF, again repeating the steps that we had, and I got 0.4. So I take 60 times 0.4, I got 24. I go to my node 3, right, which got 40 data points. I'm going to split on price, and I got an information gain of 0.2, right? So I will take 40.2, add it up, and then I do the same thing for 0.4. When I got 30 data points multiplied by 0.1, which was the information gain, I added to 3. Now I kind of group it together because I had 2 PSFs, right? So I can just add up those values. And then I got a value which says elevation importance 30, PSF importance 27, price importance 8. Now, what this essentially tells me that elevation becomes a key feature that gives me a lot of value, right? And if I end up normalizing this, which is I sum it up to 1, which means that 46% of my accuracy is attributed to my feature elevation. That's not the right way of thinking about it, but just to kind of help you put some context around it. So your elevation is the most important feature in your decision tree, followed by PSF, followed by price, right? And when you have a lot of values, your feature importance will get a nicely, a kind of a sorted chart. So this is your feature importance, which tells you how important that feature is based on how many times or how many data points it was able to split. Make sense? Do you get the idea of feature importance? Or do you want me to repeat feature importance? How are we calculating information gain? So whatever value that we got here, right, which was the Gini itself, that's my information gain at that point in time. So so this value is whatever information gain that we had. we just got it from there. Does that make sense, Ankit? Okay. So basically, I'm using that information gain and how much data gets split. So that gives more weightage to a particular feature. So that's how you kind of weigh certain data points more, certain data points less. So this shows you the attribute and what feature is important for that decision tree. Yep, it's occurring. I mean, for this example, just for demonstration's sake, I, I deliberately picked it, but assuming I had taken a random feature selection, it just so happens that TSF will occur randomly twice. And you will see across a lot of decision trees that a particular feature gets used multiple times. Because think about it, right? When you're kind of going down and down the decision tree, like you're going down the depths of decision tree, now the number of data points that are available to split is much less than when you started off. So it so happens that at that remaining data points that you're trying to work on, ESF or any of those features that got used previously has been kind of worked out before. So that becomes your feature importance. Make sense? How do we calculate this if the max features is greater than 1? No, so max features doesn't say uh, how many features will I use. I'll still use one feature, right? But how many features that get evaluated to pick the feature that's going to be used for that split. So I'll repeat. So when you set a max value of, let's say, n is the number of features, attributes, variables that you have in your data set, right? If you set it at n, it's going to use all of them. Now, when I'm deciding, so let's say for my node 1, and for example, say I have elevation, TSF, and price, I have all three of them. So I'm going to do that 128 calculations for all of them. And then for each feature of that 128, I'm going to pick the one that gives me the lowest. So I'll have one Gini index that's lowest for elevation, one Gini index lowest for TSF, one Gini index lowest for price. Across all of this, I'm going to pick the one that gives me the lowest value. So let's say in my example that I have, I got elevation before. So elevation becomes my split, right? So max features kind of puts a limit on how many attributes or how many variables or how many features that you're going to use to make a decision at each node. Does that explain, Joanne? Okay, so that's the idea around feature importances and decision trees. Now looking at the time, right, we are almost at 9. Do you want me to continue? There is another example of ensemble modeling. Again, there is a worked out example, so it will take about another 45 minutes. Are you guys okay that we can go up to 9:30? I'll make this recording available. So for people who cannot continue, oh, quite a few are not comfortable. Um, all right, let's just do a vote. Send it to you. Just a moment, setting up a poll. No, I mean, I can make the recording available, but the fact that, you can ask questions and doubts, which is what this idea is about, right? Keep it interactive, so that you guys are engaged. Otherwise, it just makes it very hard, to, work out this logic, because the ensemble modeling is going to be, something interesting and useful as well. So I've just started a poll on Slack. Just click one or two, which will tell me yes or no. Whatever is the majority, we'll go with that. All right, looks like yes is winning. I'll make the recording available, and what we can do is go through the recording, and then if you get stuck at any point in time, feel free to ask the questions, and then typically within a day or two, I will respond to those questions. So post your questions on Slack. Should be easy. Stay with me for a while, as much as you can. I'll try to kind of cover it um, uh, on the classified design. The concept is simple, but again, I have a worked out example for all of you guys. All right. So, wisdom of crowds, there are a lot of ideas around this where, or, for example, even, as kids, we had a story where, a farmer had three sons. Both of them were always fighting amongst each other. And, one day farmer was tired with his sons always fighting among him. So he said that, all right, each one go uh, get get a stick, and each one goes get a stick, and they try to break it. So of course it breaks. Then he takes all those broken sticks, six of them, and then he tries to kind of bring them together, and then it's harder to break. So the same idea goes into the thing of wisdom of crowds, where you say that each model that each person is a weak learner or a weak model in itself, but together they can bring a lot of concepts around it. And same thing for Wikipedia, for that matter, right? Nobody is an expert on everything that's happening on Wikipedia. Sorry about this. Nobody is expert on Wikipedia, but there are a few guys that are good with something and they kind of build their model. So the same concept goes into building ensemble models as well, right? Where you are going to say that, okay, each model in itself is not going to do a good job, but together they will do a very good job of doing your classification. So the idea in this is that each person should have diversity of opinion, right? So each one should be building your model individually. Independence, you want to make sure that nobody's influencing the decision. People are able to draw on specialized knowledge, which is about decentralization. And then I want to be able to collect all this information together and form a way. So in terms of aggregation, right, when I want to kind of convert it into a collective decision, what are the different ideas that you can think of where I can capture the knowledge across all? and come up with a sensible decisions, right? Something that we did just now was voting, right? So we said that, what do you think we should do now? 22 of you voted yes, rest of you voted no. So of course we are going to go ahead with yes, right? So basically I kind of, in a way, kind of did voting. Can you think of another way of where I can capture a decision across a group? What are the other ideas that I can use? Post your message on Slack. So my question is that when I want to collect the decisions from a group, uh, one way to capture a decision is majority, where I go and ask for vote. What are the other techniques that I can use to capture the collective decisions of the group? Random sampling? No. Now I want to take everybody's opinion, so I'm not going to do sampling. So I want everybody in this room or this meeting to have a voice. So poll, yep, poll is another way of doing voting. Yep, survey, yep, you can do survey, equal weightage. Yep, so I can, take the decisions of everyone and divide it by the number of votes that I get. So these are the two quick concepts that you can think. So I can take voting, right, where everybody, the majority wins, or I can take an average of everybody's decision, right? And then those are the ideas around ensemble. And ensemble are pretty good. So Netflix competition is one of them. In the interest of time, I'm going to skip Netflix. There's a very interesting story I would encourage you to go and find out. Specifically, what was happening with the top two winners, right? They submitted within 20 minutes of each other, both of them getting the same score, right? So go read about them. It's a very fun story, something that you kind of do it. So what we were doing before is, with the decision tree, we were trying to build a strong learner. So a learner that's going to be very, very accurate. And the idea of doing ensemble is, okay, I don't need very strong learners. I actually want weak learners, which are going to be better than random guessing, right? Slightly better than random guessing. So if, as long as I have that sort of weak learners, I have a weak model. And there is mathematical theory around that, but we are going to skip it for now. So now let's say, I had two class plus one or minus one. Everybody built their own decision trees based on random sampling, random feature building, and most of them came up with one. So I can say majority wins and work that out. In this one, I couldn't do average because, I just had two classes, but there are situations when you can do up with average, specifically in terms of regression. When you're doing with regressions with decision trees, that's what you end up doing now. Now, what we just learned was an idea that's used around bagging, which is an acronym which stands for Bootstrap Aggregation. So how does it work? Is that it employs a very simple way. I can do voting or averaging, depends on each one of them. But remember, each model gets an equal weightage, right? So it's not going to be any different. Now, what I'm going to do is I'll build different decision trees. Right? In this example, let's build it by decision trees. I'm going to build different training sets for training each decision tree. So I'm going to sample randomly. And remember, this is going to be with replacement. So the same value can occur in a set more than once, right? So I'm going to sample a certain number of values, build a decision tree sufficient enough, and then repeat that step again. Sample values, make a decision tree, and again, there's no necessary that you have to build a decision tree. It can be any algorithm, right? Now I keep doing that over and over again. So after a certain point, I'm going to stop. Then I'm going to combine all the classifiers and then take those values and say, okay, here's an average value, either by majority or average, depending on the problem that I'm trying to solve and the suitability of that problem to those things. And that's an idea behind building ensembles using bagging. Is this part clear, how this algorithm works? Post your message on Slack if you have got it, or I can repeat it again. Why does each model get equal weight? Because there is no way of determining and saying one model is better than the other. So your easiest way is give everybody an equal weight. So there are no separate validation sets for each tree. So you'll build this whole model, your whole ensemble together, and then you will use your validation set across all of these three. So when you build a ensemble model, which is consisting of various trees, that model itself is one model in itself, right? It's made up of small decision trees or small algorithms, but I'm not going to separate them, and I'm just going to kind of consider it together. So now, okay, so somebody asked me to repeat it. So let's say I have 1000 data points going back to the housing data sets with 7 features. So now I'm going to build a decision tree, let's say with 100 data points, right? I'm going to sample 100 data points with replacement. So once I pick a value, that value is also eligible to be picked up again, right? So I'll build a 100 data set, 100 a data set of 100 data points, build a decision tree. I'll go again, sample another 100 data points, build another decision tree. And I keep doing that over and over and over again, right? Depending on, and that's a factor that you can set up, right? So the number of trees that get built is also something that you can control. Yes, so yes, we are taking different samples for each model, and that works out very well in that favor. So the idea is that you build weak classifiers, a lot of them, and then combine them together to build a stronger model. Is that clear how Bootstrap aggregation works? What does replacement means here? So by replacement, so when you have, in our example that I gave before, so I had 1000 data points, right? And I sample 13 of them. I sample 100 of them. So when I sample the first data point, I put that data. So let's take a simple example, right? So let's say you have a bag which has white balls and black balls, right? I have 10 white balls and remaining 90 are black balls. So when I, without looking, I sample, pick out one ball from the bag, and I notice that it's white. Then I put it back in the bag itself, right? So my bag at any point in time always has 100 balls at a time, right? So I'm not going to keep reducing it over and over again, right? So that's what is meant by replacement. Lawrence, is that clear? Cool. So, so this is the idea behind Bootstrap aggregation. And then, all right, so, right, so let's go back to Scikit Learn, and then let me look at another decision trees. User guide, ensemble methods, and then let's look at random forest classifiers. Right, so now let's go back and look at how random forest is built, right? So this is the algorithm, a bootstrap way of building decision trees is one of the ways of looking at random forest, right? So this was an algorithm that came back in 2001. So it's not that old. And let's look at some of these criteria in here. So the first one we have is N estimators, right? So this says Right. So the first one that we have is n estimators, which says, how many decision trees that I need to build. The default value is 10. That's something that you can control, right? Criterion, again, something that we did before. Max depth, something that we did before. Min sample split, min sample leaves, something that, which is again very, very similar to what you were doing in a decision tree, right? Bootstrap, right? So Bootstrap, so when you were sampling 100 out of the 1,000, right? That concept is called Bootstrap, right? So the Bootstrap, when you set it as true, it's going to kind of sample it. If you set it as false, the whole data set is going to be used, right? The next comes is out of bag scores. What is out of bag? Out of bag is the idea that I can, the samples that never got picked up for a tree, I'm going to use that to figure out that, hey, how good that tree is. So basically, I just want to make sure that I'm generalizing it well enough. And that's a concept that we end up using. Now, I want to say over here, right, n jobs. So it says number of jobs to run in parallel, both for fit and predict. Fit is when you're kind of building the model, right? Why do you think this factor is here? Why does n number of jobs is important or is one of the attributes for building a random forest classifier? Post your answers on Slack. Space consumption, no, not quite. It's nothing to do with space. Think about how this algorithm works and how each tree is built. Makes calculation faster. How? You need to explain me how is the calculation faster. Yeah, of course, it's going to do it faster when you use multiple processes. Randomizing, no. There's nothing to do with randomization at this point. To use all the memory, no. For calculation, no. Yep. So RTM Sandeep got it right. Think about it, right? When you did a sample, you did your sample by replacement. So once I've built a sample, I can pass it off to a processor and let's say, let it build that tree. There is nothing in that sample that gets used by the subsequent trees, right? So I can keep sampling 100 data points and all my trees, if you have 10 cores, I can train it independently, right? Because I'm doing sampling, um, uh, which is by replacement, and I can build 10 trees, 13 trees, depending on the number of cores that you have. I can build it independently, right? So that's the concept. That's why you get this number of jobs equal to a factor that you can set, right? And then again, because there is a random state, you can kind of work this out. Verbose is like, it just kind of prints it how it works. Warm start is that, if you have already built a tree and you set warm start equal to true, it will keep on working with the tree that is built initially, right? So it's not going to start from all over. So let's say, you got to a certain accuracy and you want to kind of go back and see, hey, if I add more trees, will it improve or not? So instead of rebuilding that whole tree set again, you can set warm start equal to true, which means it will start off from, let's say, in this example, you started off with 10 trees and you say, okay, let's go and build 20 trees. It's going to start with that 10 trees that it has already built and add 10 more to it. So it will just add more to it. It will start from where you left off and continue from there. So it becomes a very good example when you are trying out with things and progressively you want to kind of work out your accuracies. This becomes the best way of working this out. So this is something that, how your random forest works, right? So now, do you understand how random forest works using bagging? Do you understand random forest, how it works, right? It's based on very, very simple criteria. Starts with decision trees and then keeps adding things. So Connie, a little, where are you stuck? Let me know. If you have any questions, let's post it. Now, the only variation in here is going to be extra tree classifiers, right? Where the difference is that instead of providing that split, right? So now the missing point is now you no longer get the best split or the random split. So over here, the split is always going to be random. And one of the other things that it's going to do is your bootstrap, right? So it's always going to be set as false. So compare your random tree where you got an option of, okay, let me go back and then put it on a separate page so that we can cycle between the pages. Right, so my criteria was Gini. I could set up the feature it's there, and the only difference between an extra tree classifier that it's going to use Gini, but that split is going to be random. So that's the difference between a random tree classifier and an extra tree classifier. All right. So I have the algorithms here: number of trees to grow, the number of variables to split at each node, and in here, sorry, let me go to screen. And then, I can keep increasing, decreasing the weight across each one of them. Now, there's another idea around, building trees, which is called boosting. I'll cover this in the next session so that, I'm not kind of confusing you with too many ideas around this. Now, again, the concept is very, very simple on this. We'll cover it later. But before we meet up next time, right? I think next time we are going to meet up in 2 weeks. What I want you to do is you have a Kaggle competition. Now you understand decision trees, random forest classifier, and extra tree classifiers. So go back to the data set that you had, play around with these different factors, and make your submission on Kaggle and see if you are able to improve it beyond your default values. Okay, your homework for the next time that we come along is going to be do your Kaggle submissions with your decision tree classifiers, right? So look at decision trees, look at random forest, look at extra tree classifiers, and make your submissions. I hope that with the knowledge that you have gained, now you start making better decisions in working that in trying to figure out what's the best way to increase the accuracies of your models. Okay. All right. Any other questions? The data set is the same as what we used in Kaggle last week. So we'll continue with the same data set. So I'm hoping that as you learn different techniques, different ideas, you keep on using that as your baseline and keep working and improving the model. So SPM, let's take it offline on the NLP channel. Next week, I still want to do, again, do you want me to go through different classifier models or go back to NLP? So I've posted a poll again. So which classifiers? Okay, NLP. Yes, NLP, again, because we are doing sentiment, we are still dealing with classifiers. And I thought that learning about the algorithms might give you better insight of how these algorithms are working. So instead of blindly picking up values or letting a optimizer pick those values for you, at least I was thinking that it will help you build an intuitive understanding of how some of these concepts are built, and then kind of go from there. Yes, we will go back to NLP after these things. So this is, like I said, right, we will keep it flexible. So the schedule still remains, but, depending on what you want to do, we might just kind of link it. Um, I'll post the Kaggle link after this, or somebody who has it handy can invite folks who are not on Kaggle. So somebody post the link, or I'll post it after the session. All right, so most of you want to go back for NLP. Um, there's an invite, so I'll post the invite link in this. How do we list out the best features for a given data set? Uh, so once you build your classifiers, right, one of the things that you will see is feature importances. And that's something that you can pull out of these models and then um, build a chart on this. So you will have, so I'm going back to my um, Scikit Learn. So one of the attributes that you can pull out from the tree is going to be feature importances. So you can just pull this value out and plot a histogram or a chart, and then you can see all the best features that have been used. If you sort it, you can see the best features that have been used. So that's something that you can play around with it. All right, so most of you have asked for NLP. So for the next sessions, we will go back to embedding modules, and then let's try to understand the concept of embedding. But till then, I would still expect that, keep practicing around using what you have learned today. Don't forget your Kaggle submission. The idea is that, hey, you get this practice in a safe environment. You can ask questions on Kaggle and then work through that. I'll be posting the slides again. So there are concepts on regressions and other advanced models like locally deep SVMs and others. So for those who are interested, go through the slides. Let me know if you have any questions. We'll be happy to do it. The Excel slide that I have posted also does the boosting as an example. So I have practice questions for you as well as the solutions for them. So for those who are interested to learn these algorithms, go ahead and do it. If you have questions, post it on the forums. For the next session, let's go through embedding and understand how embedding works, how can I make use of it, and what's the theory behind that. Again, one more thing which I would request. If this is the first time I'm kind of doing this. So if you like this format, let me know. If you have any feedback, either you can put it on the forum or Slack, or message me separately if you have something critical to share. Let me know. This is the first time I'm doing it as streaming. So I don't know how you receive it on the end. So would really appreciate your feedback. If it's good, let me know. If it's not, let me know what I can do to improve as well. So with that, thanks all. Really appreciate it. I hope this was interactive enough. And then next round we continue doing that. All right. Thanks all. Let's think about algorithms. Maybe towards the end, let's come back and revisit some of these algorithms. I'll share the slides, go through that. For those who are interested, I'll set up a separate meetup, and then let's go from there. And I really apologize for the mishap with YouTube. I think this is the forum that we'll continue with. We'll continue to use Zoom, and that's the concept, that's the format that we'll stick with it for now. All right. Thanks a lot. and have a good night. And let me know your feedback. I'll kind of wait to hear from you. Hope you guys had fun. Take care. Bye-bye. Next time it's going to be embedding.